finished the last lesson, lesson 2, by listing off these 6 things that we've so far been able to intuit, document, and necessarily imply. But one thing we didn't really state clearly is what we don't know. And the principal thing we don't know about Earth intention yet is what's causing it to happen. We have no visible force, no present agent, nothing from within the material world that we can see other than the objects themselves are moving. We don't see the cause behind their movement, and this is very important at this point to acknowledge that for all that we do know, we know certain things about the nature of falling objects, but we don't know the nature of the affect of falling objects. So we just need to keep our minds open and our ears open, as it were, for listening for the approach of something like a cause. And that cause should be implied by the things that we know. So this will be a next level implication, a summary implication. It will reveal to us the nature of the cause, though it may not actually be able to reveal it in itself. It will reveal itself through the nature of the expression. And that's going to be an important part of this conversation. And we will begin to answer that question more fully now by considering objects in more of a state of dynamic motion. And we see that expressed here quite clearly when we look to categories, or the 2 species of a formative intention, in this case forming the Earth, and in this case forming the Moon. And it is agreed that there is such intentions. We know there is one for the Earth. We know that the Earth is formed into a sphere by it. We look at the Moon and we see it as a sphere and assume that it has a similar formative structure, some kind of intention. Do we know that it's exactly the same as on Earth? Well, of course we don't. So it could vary, and it could vary according to mass, and that's the hypothesis that is mostly accepted. There could be various ways in which it varies, but the nature of the fall, we have to determine whether or not it matches the material explanation or not. And so the intention is here. We're under these 2 categories of intention. And then we have these 2 formulas that describe these falls that are graphed here. We have 2 falls, a fall for the Earth and a fall for the Moon. And this is the fall for the Earth and the fall for the Moon. We select for any given du tu on Earth, we're going to graph a line that looks like this. And for any fall on the Moon, we use 1/6 the d of the Earth, and time remains the same. And so we graph a line that looks like this. So again, we remain in the general. It's for any tu du we might choose here. This is going to be the case here, that it's 1/6. And then that works out here on the graph. Now this graph is saying that space is running this way. That's intuitive to us because we're talking about fall. So it makes sense that our distance is moving this way. It's distance, but space is being measured here and time here. So we're not looking at objects that have been thrown or something like this in this instance. We're looking at a space-time correlation and seeing how that expresses itself in graphically like this. And there's quite a bit that can be learned from this method, including what we're looking at here. We're not looking at, one ball, as it were, being thrown harder than the other ball. We're looking at a correlation between 2 conditions, two different environments entirely. One supposedly on the Earth, or one that we know is on the Earth, I should say, and the other is the one that is said to be the case for the moon. If we look at the animations, we see the idea expressed a little more clearly, whereas we have these are the time coincident locations of the ball. We see how the Earth ball is off the charts pretty quick here, but we see that this is what the time difference is. See how long it takes the moon one to do its thing. Even, this is what we need to understand that we should be expecting when we are talking about the conditions on the moon, and then the gravel being churned up by the vehicle. That's the kind of delay we should be expecting. And we see here, we're just making a coincident time to show that if we take the formula Fe equals du times t squared, and we convert it for answering for time, down at the bottom here we get t equals the square root of the fall divided by the unit distance is equal to the square root of 6, because the fall is equal to 6 and the unit distance is equal to 1, and that gives us a time location of 2.45. We can change the understanding of the graph as well by changing our space measurement to being the altitude measurement, and changing time into range. Now, in a sense, both are measuring time, but this is going to measure time differently because the motions are going to vary as they go down this way, each time unit. So time is not measured evenly, though it still has its locations on the falling. But here it's measured evenly. And what we're assuming is that we have a velocity or a vector. We see now that our lateral motion can be seen as a vector, which we can write like this, which means that it's a vector of 1d per t. When we're measuring in the velocity, the range velocity is equal to d times t, so that's 1, and at 0 degrees from horizontal. So this is going to be, if it were able to just fly straight through the air without falling, it would be clocking just like our time was kept before, except now it's physically moving through space in these two different spaces, and you can think of the animation again and what that implies in terms of objects moving in these two different spaces. But to do so, we have to make an assumption of absolute time, absolute space, and absolute matter. The reason for this is that the only way we can say that IE, the Earth's intention, is different than IM, the moon's intention, in this way that the moon has 1/6, is if the two can be measured across each other in a meaningful way. If things are just smaller here or just different, then it's not the same space. You can't equate them. You can't have a conversation about them being places that have common enough rules such that you can say that they exist within the same larger realm, such as the what we often call the solar system. Are we physically in the same space, or are we looking at something quite different? Well, nobody is saying that these are not in the same space, but this difference, we have to have some standards of which we're measuring that against, and that's what this here. We have an absolute space-time graph we had before, and now we have it graphing the motion of our objects in comparison into an absolute space-time. So we have to assume absolute time in order to say that the ball is falling a different distance per time. So that's the commonality between these two things is Tn. And that's what we say here. Absolute time is equal to the time on Earth, and that is equal to the time on the moon. If we're saying that on the moon we're counting time differently, then what are we saying? That there's 1/6 of that. Now, this also implies absolute space. So if the time is going to be, if we're going to say that a certain object is in a certain location compared to another object in another location in space and time, then we have to have these things be absolute. The time has to be absolute, and the space has to be absolute. Otherwise, there is no conversation like this, and there is no sensibility about talking about a place like the moon having 1/6 of the gravitational energy or the intentional energy of the Earth. And absolute matter, that's in this case so far we're not really dealing with matter in terms of as matter, because all objects so far we have only objects moving at the same rate as any other object, and we assume that if this mutual mass attraction universe, and that's the one we're deciding whether or not this exists within, this difference between the Earth and the moon, we must assume that on the moon all objects of mass are also likewise moved at the same rate regardless of mass, because that's it seems to be a general truth. So we assume that the moon would have the same conditions, only that things would be slower, as we see here. And we see there's something interesting which we'll get into later that happens here. We have this line here. We can draw a 45-degree line through, and we can say that at the moment that our range location is equal in distance traveled to our fall location, creates a 45-degree line, because it's one this way and it's one this way. It took the same amount of time to get there. So there's a unity here between the two systems, and we see up here in the Earth system that unity happened at 1, whereas on the moon that unity happens at 6, because it takes 6 times the amount of. So we have this notation here, which I prefer. This is another notation which can be used. We see here this unit fall is what I call this, and we'll see something interesting about this unit fall. That at this location they have both traveled the same distance, but it's not possible that at this location, in terms of the velocity of the ball, is going to be greater than the velocity this way. That the descent velocity will be greater, because it has had to make up for the slower fore portion. It begins traveling at much slower than. It's somewhere along the line it's going to be traveling the same velocity as 1d per t. And then by the time it gets down here, it's going to be traveling greater. And that's in both cases, in both unity. This is now, I'm just looking at this as the unit case. Anyway, there's a lot that we will look at in a little bit. I'm trying to introduce it with the least amount of numbers on it to begin with, and just to see the forms, because we see this difference. But this can also, if we're ignoring this line, this can also be seen as just the unit form of this formula, this generic formula, such that the ball could be traveling at a range velocity of 1, and this could be in 6th, measured off in 6th, that could be 1, and by the time it's reached also 1 going this way, it has this coincident space-time location of the two formulas. So I think that's enough by way of introduction to this was an infill, so I'm hoping whatever follows this follows with at least some modicum of smoothness. I will try to edit it in a way that works that way. This some of this we're learning is just purely for fun. It's also just to see what we can learn from this method, this analytical geometry, which is what this really is. It's a tool for analytic geometry, and you will see when it's put to use in a fuller way in the next video, or in some video to come up. But just to think about it right now is good, just to get the basic idea in our heads before we become overwhelmed with some of the detail that comes out of it. But it's this nature of things that I hope it's clear that though this may be novel, it may not be novel. I actually don't know. I'm uncertain whether or not anybody has ever analyzed gravity in this way, or whether anyone has analyzed exponents in the way that I will do, because that's really what this is. This is an exponential, it's a parabolic arc, it's an exponential graph, because this is an exponential formula. Whatever this is equal, it's going to make this shape change, but it's going to be the basic shape. And you see, even if it's accelerated or decelerated in this case, it still makes the same form. It still has a unity. So we see a beauty of symmetry between these things. If they do exist, there is a correlation there that is plenary. It is not in any way sort of haphazard and uncertain. So anyway, we'll continue the bulk of the video now, where I begin with an older iteration of the graphic. So it's here, I've made a slight change here. Instead of referring to t as the unit time, even though it is measured in unit times, it's the current, or the nth iteration that we're looking at in terms of finding the vol. So the unit, the distance unit, always remains the same, whereas time continues to march along. And in this case, time is also measured out as range, because we have our velocity of range, or range velocity, is equal to the distance unit, which are these squares are broken down into, times just t to the nth. And in this case, it was t to the nth squared, and that's the difference between these two lines. And that's how this line is formed, I'm sorry. If it were just simply, if this were simply our formula, and it were a time-space formula, and it was this one, it would come through like this. That is, if the motion was this way, but we're measuring it this way. And so we're counting time this way, so we have a range velocity at some instigation here that is 1d per t, so it's just moving along straight. 1, 2, 3, 4, 5, 6. Whereas here, it's 1, 2, 3. You can see how fast, much faster it gets. By the time we're here, we're going to be at 6 times 6. We're going to be at 36 times this difference, this distance from this point down. So we can see the nature of that change. But one thing that's interesting is that in this projectile stuff is that the range velocity it's never affected by the Earth's intention. So whatever is pushing down, this just is, if there was no Earth's intention, it would just still carry on at the same velocity like this. Likewise, if it's at an angle up or even vertically, it never cancels it out, or it just overwhelms it, because it's a growing quantity. It's getting more and more and more, whereas this is not. This is just running consistently, or constantly. So we have this first intention for Earth, counting along, going down, and then we have that for the moon, also with the same range velocity within the unit, but it's going to be traveling down 6 times slower. So with the same intention, this is what it would look like on the Earth, and this is what it would look like on the moon. And so that is again, we're looking back at that video or remembering back to the video. Is that anything like what we saw there? It doesn't seem like this in any way conforms to that difference. So we can switch the graph and look at it in this way as well, where we have our altitude again is running up and down, and our range is running laterally. In our case now, our moment of instigation is here rather than from the top falling down, because now the point of apex and then the fall after that is reached symmetrically from the throw being curved back towards the Earth by the intention. You see each of these portions increasing according to the t-squared formula. And we see that on Earth we have a motion. Let's say we have a unit motion on Earth, the same as we had before for falling objects. So if it goes this far on Earth, then that same motion is going to instigate this much motion on the moon. So we see the 6 times difference really makes a big difference. And we could further develop our comparison to this line as well. And we will further, we can see that if we can make this comparison in that this outer line is 6 times the size of this line in terms of event spread, which is to be expected under the 1/6 intention on the moon as hypothesized. And we see here, if we have the thing spinning, we saw, from the scale of the vehicle, we saw quite a few things that were under a fair amount of effort. I mean, on Earth, it takes quite a bit to cast up that kind of stuff. It takes some burning in the gravel or the sand or whatever. Same as we saw in the dune buggy film from 1970. But this here, like the same kind of effort, which seemed when the film sped up to be just kind of normal, this kind of thing on Earth. They might have got as high as twice as high as the guy sitting in the buggy. This is 6 times. This is 6 times. This is what those kinds of efforts should represent on the ones that we saw happening in the film, scale-wise to the tire, say twice as high as the tire. We saw those often happening on the return trip. 6 times. The stuff going out of the back of the thing on the moon should be like this, kind of like wildland stuff, not this slightly slowed down. We will do a little bit more of a detailed critique in time. But so anyway, I introduced this here. We'll see what part of the video that I come in on. Yeah, we see if we scale in a tire here, they're probably about 18 inches, maybe those tires. Maybe they're as much as 24 inches. But anyway, so about 18 inches. So just moving along slowly, kind of spitting a little gravel out of the back of a normal car, a normal dune buggy like we saw in the dune buggy movie. In the time that this would dump from here to here, just a little spit out of gravel, this would only have reached its ascent to here, and it would continue on each time, and it would take 6 times as long. It's not that this is going faster. It can't have that kind of vision of it. It's not like this is going almost like this is going slower because this is covering the same amount of distance in the same amount of time. No, this is traveling very slow. I mean, this is 1, 2, 3, 4, 5, 6. And we have to ask ourselves, and we'll scale this right in with some of those and look at, do a more of a technical look at the dune buggy the moon buggy footage. But this is the modeling that we're to necessarily expect. This is not a hypothesis. This is not a maybe. This is an absolute fact of the condition if we are to take the hypothesis of mutual mass attraction as being the model with which we're trying to understand the Earth, and we're taking a 1/6 gravity for the moon. This is exactly what must be expected, same as before with the lateral motion and the further range. And so we see again an expansion of event. So every event is going to take longer to happen, but also occur over a great deal more area, such that it will go up 6 times and over 6 times. And this is part of the nature, the fascinating nature of these vector mechanics. When we're in the world and we throw an object, we just see it do its thing. We expect it to behave in a certain way, and we understand this is predictable, that these parabolic forms will take shape as we throw an object. Now this is called this angle of throw, let's say. So we're going to throw a baseball or something at this angle. This is called a vector. And the vector has 2 components to it. A vector has a velocity of the vector, and in this case that is the square root of 2. We'll explain that in a second for those who don't know what that is. And it's at 45 degrees. So it has an angle of intention, and it has a value of intention, a magnitude of intention. The way the vector breaks down is that when we're modeling this, we actually model it as how much does it go up, how much does it go over, how much does it go up, how much does it go over. And that is implied by the angle. Obviously with a 45-degree angle, that makes it nice and easy. We've got 1 over, 1 up. And so each time we are calculating it, we're saying the movement is 1 over, 1 up. That's where it would be if there was no intention pushing down, if there was no, or moving downward, if there was no vertical intention of IE or IM. So for each time interval, we calculate the motions of the object in terms of all of its horizontal and vertical intentions. So we have a horizontal intention of 1 and a vertical intention of 1. So we count that out, and we can take this shorthand route here, but we still have to count in both because we want to get somewhere, but we're also calculating this intention downwards this way each time, such that this here is bearing down, or this here is bearing down on the motion, so that we go over 1 up 1, but we come down this portion here, a 1/6 of a whole motion. We see in this, that's why we're already back down to the Earth here, because we go over, and we've gone over 1 and we've gone up 1, but we've come all the way down 1 as well. And that's why we get this very short run here, and why we get 6 times that here. But you can see with any kind of measurement, with this kind of ideal vector at 45 degrees, we see what happens. At each time interval, we have a little bit more distance, little more distance, little more distance, and more each time, because it's actually accelerating. But what you have is very strange, is that it's measured against as if it were continuing in a straight line. The energy doesn't happen at its location, as it were, each time. That would make everything speed up in a great deal. This very reasonable path that things follow is because it is being curved down, as it were, from the straight line that it would have been traveling if not under the intention. And this curving doesn't actually, like I say, it doesn't, in no way does it cancel these motions or these motions. It affects the altitude in that it's continuously gaining more and more influence against the constant influence of the intention, of the throw intention. It has a singular intention north or up. One, this is its desire to go up one each time, one each time, one each time. That's what its intention is. But this is this is pushing down more, well, less than one to begin with, and then once it is one, it's more than one, more than one. So this bends this downward by this constant intention, which is the formal and efficient cause of Earth. And also its telos. It's a singular cause almost in all aspects, this intention, this Earth intention or moon intention. But we're uncertain whether the moon has 1/6. It could be very likely that it's just a smaller body that has the same intention as Earth does. We have no reason as of yet to suppose that mass has something to do with the potency of the intention. Yes, that mass has anything to do with it. We don't know that yet. All of this said here, probably a little bit more detail than is needed, but it's an opportunity to teach something, but also to show that this is all very systematic, our analysis. It's very systematic. And it shows us what must necessarily be expected for a vehicle in 1/6 gravity, if that's the conditions for the moon. That these are the kinds of things we should expect. And that if we can slow down the film such that it just looks like a normal thing happening on Earth, that doesn't conform to this. This is 6 times greater. And there's nothing here. There's no change in lateral or vertical intention. You know, you throw a ball at 45 degrees on Earth or the moon, it's going to travel at the same rate if you throw it at the square root of 2 or at the range and altitude velocity of 1 and 1. It's going to move just as fast. What is going to look slow only as it's coming down, and that will give a sense that it is moving in slow motion. But it's actually moving at the exact same rate. But there's nothing about, like, the car moving along is not going to look like it's moving in slow motion, the dune buggy. There's no reason for it to move in slow motion. So we should see a contradiction between visually we should see a contradiction between the motion of the vehicle, which would just be moving at whatever rate the thing can move at. What is it moving, 5 to 10 miles an hour maybe on that rough terrain? It's hard to tell. It's bouncing around pretty good. But there should be nothing about its movements that look artificial other than what's coming out of the back of it. It should look like the vehicle's moving at a normal speed, but this is moving at 1/6 the speed. And that contradiction should be very clearly visible in the footage. And we'll call that a wrap for this time. That's plenty of work on introducing projectiles and how they apply to our conversation here and how they apply generally. So for this time, thanks for listening if you've come this far, and Teleologic Jones.